Okay, so I want to talk about G, H, and I. G and H are actually closely related to each other. Because one of the things we saw when we did VSEPR theory is we had some double bonds in some of our molecules, right? Well, first of all, we noticed when we were pulling and doing the tugs of war, even though somebody had 2 ropes, they pulled the same amount as somebody that had 1 rope. Well, Lewis structures would tell us that are there really any of those molecules that actually have double bonds? Well, some of them, yes. Carbon dioxide has 2 double bonds. Okay, but some of the ones where it was like a trigonal planar shape where there was only 1 double bond in here, is that true to only have 1 double bond?
No, resonance.
Yeah, we know in resonance theory that that double bond is sort of shared throughout the molecule. Okay, and actually, this hybridization concept is going to help us think about what does that actually mean to share that double bond. And we'll get into it from another perspective called molecular orbital theory. All right, so hybridization and hybrid orbital. The reason that this was created was when we look at a molecule like methane with a tetrahedral shape. What are the bond angles?
109.5.
109.5. Okay, but to make a bond, what are we doing? Sorry, to make a covalent bond, what are we doing? Sharing our electrons. How do we share electrons? Well, where do electrons live? They live in those little wave functions that we call orbitals, right? Those S-shaped wave functions, those P-shaped wave functions. Well, that's really where they live when the atom is by itself. Okay, so in CH4, in methane, the carbon in the middle, it has in its valence shell, let's see, carbon is 1s2, 2s2, 2p, 1, 2. Okay, so the valence orbitals are the 2s and the 2p. What does a 2s look like?
Sphere within a sphere.
Sphere within a sphere. Okay, I'll just draw the outer surface, right? So sort of a spherical 2s orbital, and what do the 2p's look like? Kind of like peanuts, kind of like figure eights, right? So there's 1, 2p. Where are the other ones? One straight up and down. And one sticking out of the board and back behind the board, right? I can't draw them on a 2-dimensional surface. Okay? But I'll just draw 2 of the 2p orbitals, and I should be able to illustrate the problem with the bond angles in methane, 109.5. Because these orbitals, if I try to make bonds with, say, hydrogen, like in methane, right? Here's my carbon. If I try to bring a hydrogen in here, in order to share those electrons, we have to overlap the orbitals. What's the valence orbital in hydrogen?
S, 1s.
It's a 1s, right? That's the only orbital in hydrogen. Okay, and that looks like a sphere. And so as they overlap, we create this region of shared electron density that helps hold these 2 atoms together. Right? We're sort of combining those 2 wave functions, but the combination is going to give us more electron density in the areas where they overlap. So we'll have more negative charge here, which is going to pull those 2 positively charged nuclei together. All right, well, it's CH4, so where's the other hydrogens going to go? Well, I could put a hydrogen down here and overlap its 1s with another 2p in the carbon. And again, the overlap here, that's what's causing these 2 to stay together. This shared electron density. Okay. But what is the bond angle right here? Well, these are perpendicular to each other. So if we try to overlap a 2py with a 2px, we would expect this bond angle to be 90 degrees. And if I think about the orbital that's sticking out of the board, maybe we call it the 2pz sticking out of the board, I could overlap a hydrogen there, but it's still going to be 90 degrees from either of these. And how do I overlap the fourth hydrogen? I'm going to stick it in, squeeze it in here at the 2s? Doesn't really make sense. So in order to account for these bond angles, and in order to account for the fact that when we try to measure the bond energy, when we try to break apart CH4, we can measure how much energy it takes to break those CH bonds. If the hydrogens were really overlapping with 2p's for some of the bonds, and maybe with the 2s for that last bond, well, we know that 2s is at a different energy than 2p, right? From PES data. There's slightly different binding energies. So we would really expect that maybe the bond here with the 1s of this hydrogen and the 2s of this carbon, we would expect that this have maybe a slightly different energy than this bond. But we don't see that. We see 4 exactly equivalent carbon-hydrogen bonds. So this theory was proposed back in the 30s, I believe, where we say, okay, something else is clearly happening. These atomic orbitals that we got from solving the Schrodinger equation can't really still be like that when we make methane. So perhaps those orbitals do something different. And what they do is they hybridize. What does hybridize mean? To combine or to mix, right? A hybrid car is a mix of a gas-powered car and an electric-powered car, right? A liger is a hybrid of a lion and a tiger, right? It's pretty much my favorite animal. Okay, so what does it look like when we mix these together? I can't draw it on this board. I don't have the skills required. So I found some videos that do a decent job of explaining roughly what that hybridization is going to look like. So I'll show you those, and then I've got another program that can do something interesting too.
To account for the millions of molecules with tetrahedral shapes, the model proposes that the central atom undergoes sp3 hybridization. For example, in the carbon of methane, the filled 2s, 2 half-filled 2p's, and empty 2p mix and become 4 half-filled sp3 hybrid orbitals. The model describes
So there's the atomic orbitals.
methane this way. In the molecule, the carbon's 4 sp3 hybrid orbitals point to the corners of the tetrahedron. The H orbitals overlap them to form 4 CH bonds that are 109.5 degrees apart. For other shapes within a given electron group arrangement, the model proposes lone pairs in one or more of the hybrid orbitals. For example, the trigonal pyramidal shape of ammonia arises when the 2s and the 3 2p's of the central nitrogen mix and become 4 sp3 hybrid orbitals, one which is filled with a lone pair. Here, we visualize the nitrogen atom undergoing sp3 hybridization. One of the tetrahedrally oriented sp3 hybrids is filled with a lone pair, and the H atoms overlap the other 3 to form 3 NH bonds.
So it's hard to see exactly what's going on here, okay, but this is this shape where the lone pair is up here, right? So we have that tetrahedral geometry, which means we have 4 things attached to the central atom. In this case, there are 3 bonded atoms and 1 lone pair, but we still need some orbitals for those electrons to go in that cause the bond, and we need an orbital for the lone pair electrons to live in. Okay, so it's still sp3 hybridized. When we say it's sp3 hybridized, that's just a shortcut notation of saying how many of the individual atomic orbitals mix together. If I need 4 orbitals, 3 for the single bonds here and 1 for the lone pair, I need to mix together 4 atomic orbitals. I always start with an S because that's the lowest energy orbital in that subshell. And then if I have to get 4 hybrid orbitals, I'm going to have to mix together 4 atomic orbitals. So I have to mix the S with a P, another P, and a third P to get 4 atomic orbitals to mix together to make 4 hybrid orbitals. So because we've mixed an S and 3 P orbitals together, we call it sp3. If I mix together an S and only 2 of the P orbitals, we call it sp2 hybridization. If I only have to mix together an S and a P, we call it sp hybridization.
In the case of water, with its V shape, the model proposes a situation similar to that for ammonia. The 2s orbital of the central O atom mixes with its 3 2p's and becomes 4 sp3 hybrids. But now, 2 of the hybrid orbitals are filled with lone pairs. In the water molecule, the oxygen has undergone sp3 hybridization. 2 of the sp3 orbitals are filled with lone pairs, and the H atoms overlap the other 2 to form 2 OH bonds. To account for
Sorry
the
for that
millions
glitch.
of molecules with tetrahedral.
Now, the way that they drew these sp3 hybrid orbitals is not really all that clear. So there's a nice program that we've already seen before. This one. Remember when we were first doing that wave function simulation orbital viewer? I showed you this because this is sort of a 2-dimensional vibration. That's an analogy to the 3-dimensional vibration that the wave functions are supposed to be represented. Okay, so this was like an S, and then the 2S, as Stephen said, was a sphere within a sphere, is a 3-dimensional analogy of this. The 3S is a sphere within a sphere. That's a 3-dimensional analogy of this, right? If I just rotated this into a sphere. Okay, but what's cool about this is I can also show you P's, right? Remember how in the orbital viewer program, when you had that P shape, it had 2 different colors on it? The positive phase and the negative phase? Same idea here, right? They're showing the positive phase in green, the negative phase in red, but there's clearly some difference between the 2 sides of this wave. What's cool about this is I can turn 2 on at once. I can hybridize. I can mix together 2 different wave functions. And that's what I've done here. And if I can pause it at just the right time, okay, this is typically in 3 dimensions how we represent sp3 hybrid orbitals. Usually you'll see these hybrid orbitals drawn something like this. So it sort of has that 2-lobe shape like a P, but it's a lopsided 2-lobe shape because we're adding together that S behavior. Okay, so just like this thing is combining the sort of completely spherical shape where it's just going up and down, and the back and forth shape, adding it together to make a hybrid function, the 3-dimensional analogy kind of looks like that. It has a little small end and then a bigger end on the other side. I'm trying to think. Yeah, this picture doesn't show those hybrid. It kind of just shows the big part of the hybrid orbitals in there, but really they should all sort of look like this. Some pictures you see, I think our book has some images where they look more like what I've drawn up here. Now it says when the bond angle is 180 degrees, the central atom is said to be sp hybridized. We haven't talked about that one. We talked about the case where if the bond angle is 109, the atom is sp3 hybridized. So what would it take for it to be sp hybridized? Well, I've got a video that shows some examples there.
Valence bond theory proposes that each carbon undergoes sp2 hybridization. Its filled 2s and 2 half-filled 2p's mix to become 3 half-filled sp2 hybrids, and the fourth electron occupies the unhybridized 2p.
Okay, this is not actually sp, they're talking about sp2 hybridization. sp2 hybridization is when we have 120-degree bond angles. So what they're trying to explain actually in this one is a molecule that looks like this. This is called ethene. Each carbon has 3 bonded atoms and no lone pairs. So each carbon should have a shape that is triangular planar. Right? 120-degree bond angles. I guess I didn't draw them quite 120. That's more like a 90. My bad. Okay? But if we're just trying to make 120-degree bond angles, we actually only need to mix together an s and 2p orbitals.
Let's examine the orbital view and highlight the 2 ways carbon orbitals overlap to create a double bond. Here, each carbon is undergoing sp2 hybridization. Note how the unhybridized 2p orbitals lie perpendicular to the trigonal plane of sp2 hybrids.
Okay, so sp2 hybrid orbitals still look kind of like a combination of an s and a p orbital, but in this case there's only 3 of them because we've only mixed together an s and 2 p's. We've only mixed together 3 atomic orbitals, so we're only going to get 3 hybrid orbitals. Okay, but what happened to that p orbital that we didn't mix in? It's still there. This is the unhybridized 2p that didn't get mixed in with the others. And it's actually this 2p that's going to help us explain where this other bond comes from. Okay? Because as we bring these things together, the sp2s here are going to overlap. That's going to make one of the bonds between the carbons. But how do we make that second bond? Well, we can't overlap more than 2 electrons in this region of space right here. Pauli exclusion principle says we can only put 2 electrons in the same region of space, and we can only do that if they have an opposite spin, right? When we're filling in our orbital diagrams, we can only put 2 arrows in each box, because 2 electrons at most can fit into a given region of space, and they can only do that if we draw 1 arrow up, and 1 arrow spin down. So how the heck do we share 2 pairs of electrons between these? It's going to hopefully try to draw it.
The 2 sp2 orbitals facing each other overlap end to end. The bond they form is called a sigma bond. It is symmetrical along an imaginary line between the nuclei and is not weakened by the rotation of one atom with respect to the other. Now, focus on the 2 parallel 2p orbitals. By substituting accurate representations of 2p orbitals, you see that they can easily overlap side to side. This results in a pi bond, one that is not symmetrical along the line between the nuclei. Most importantly, it is weakened and in fact breaks by rotation of one atom with respect to the other. Thus, a double bond consists of 1 sigma and 1 pi bond. In the ethylene molecule, 4 H atoms overlap the 4 other carbon sp2 orbitals. Valence bond theory proposes that
It starts over every time. Okay, so basically, it's like we're saying that we have, in this case, 2 carbon atoms that both have 120-degree bond angles in there, so they are sp2 hybridized, right? So the sp2 hybrid orbitals are each represented by a stick here. And we've got our unhybridized p orbitals still sticking up and down out of the plane of that triangle. Right? I'll do that in this other atom as well. Okay, and then so they're saying that as these things bond, the sp2s from each carbon will overlap and form this bond in the middle, and then the p orbitals that are left, it's hard to do with this model because it's not flexible, but the unhybridized p orbitals that are left will also overlap. Okay, kind of like this. So we'll have regions of shared electron density up here and down here. They're not exactly in between the two nuclei, but if I have a negative charge here, it's going to still attract both nuclei kind of towards the middle, right? And since I've got another region of shared electron density up on top, again, both of these are going to be helping keep those two nuclei together. All right, the difference is we call the one where the density of the electrons is right in between the two nuclei, we call it a sigma bond. When we overlap p orbitals, and the p orbitals are overlapping in a region of space that's not immediately in between the two nuclei, we call that a pi bond. And he said that the pi bond is weakened by rotation. So if I try to rotate this molecule, now the p orbitals don't overlap as well because they're not along that same axis anymore. All right? It actually, for molecules that have a double bond like this, you cannot rotate them very easily. Okay? So what that leads to is, for example, if I had something other than hydrogens on here, let's say we had some chlorines. In a molecule with a double bond, whether the chlorines are on the same side of the molecule or opposite sides of the molecule actually makes a difference because they cannot easily be converted from one to the other. Because this double bond cannot rotate, I can't just do what I did before, which is to rotate this thing. If I actually cause this thing to rotate, the molecule will break apart. So this is called isomerism. When they're on the same side of the bond, we call it a cis isomer. When they're on opposite sides of the bond and you sort of have to go through that bond to get from one atom to the other, we call it trans. Trans means through. All right, anybody heard of trans fats?
Yeah.
They're not good for you, right?
They taste good.
They taste delicious, but they're the worst kind of fats for you because they're not normally made in nature. But when we make them in a lab, actually when we try to make any of
Why
these,
do we make them?
we don't try to make them. What we're trying to do is to take certain fats and change their properties a little bit. Okay, so saturated fats are bad for us, right? Saturated fats don't have double bonds. So unsaturated fats are a little bit better. We said, okay, why don't we take some saturated fats and make them unsaturated? Well, one of the problems with that is when you create these double bonds in the lab, there's no preference in creating them in terms of whether they end up on the same side or whether they end up on opposite sides of the double bond. So you're just in the process of making these fats end up with a mixture of both. And the trans, because their nature doesn't do it that way, the trans is not something our body's used to, and it's actually a more unhealthy thing to have inside of our body. Okay? You don't actually have to know about cis and trans, but the sort of idea of not being able to rotate this bond, double bonds are going to sort of hold their shape. Whereas if we just had a single bond, like if I had another methane molecule to connect here, this is ethane, C2H6. It has all single bonds. Those single bonds can rotate. This molecule can rotate in a bunch of different configurations because rotating it doesn't weaken this bond. But if I try to have a double bond in there, I can't rotate it because I ruin that overlap of the p orbitals. All right? Now, if it's 180 degrees, they say it's sp hybridized. I've got a picture of that on the notes, So I'll just show you that, and we'll take a look at it. So on the top is the one we just looked at, ethane with the double bond, and your p orbital overlap. Your pi bond is up here and down here, and the unhybridized p orbitals overlap. This is ethyne, C2H2. So we need to have a triple bond here between the carbons. How the heck do we share 3 pairs of electrons? Well, one of the shared pairs is from hybrid orbitals overlapping. We call them sp hybrid orbitals. Those are the ones in orange. There's one sp hybrid orbital overlapping with the hydrogen here. Another sp is overlapping with the sp of this carbon here. And because that overlap occurs right in between the 2 nuclei, there's a sigma, what we call a sigma bond here. But if we only use 2 of the valence orbitals, an s and a p, that means we've got 2 left over, 2 unhybridized. One unhybridized p orbital is the purple ones that are overlapping to make a pi bond. The other one is 90 degrees from that. That's the blue ones that are also overlapping to make a pi bond. So a triple bond is actually a combination of a sigma bond combined with 2 pi bonds.
So the pi bonds come from unhybridized 2p orbitals.
Mm-hmm.
So in an sp3 there are no unhybridized, all of them.
Exactly.
And then
So
an
in
sp
tetrahedral, you're never going to have
double bond.
double
or
bonds
triple
because
bond.
you've used up all those p orbitals. You don't have any p orbitals to make double bonds with. That makes sense?
Yeah.
Okay. So mostly what they're going to ask you to do with hybridization is to say what type of hybridization occurs, and fortunately for you at this point, that's a kind of memorization thing. If they give you something that's tetrahedral, you can say the hybridization is
sp3.
sp3. Even if it's trigonal pyramid, because we know that's still tetrahedral electron geometry, this is sp3 as well. Okay? If they give you something that has 120 degree bond angles, trigonal planar, you can say it's sp2 hybridized. And if it's linear, 180 degree bond angles, you could say it's sp hybridized. All right? That's basically just a memorization. The other thing you have to do here, it talks about the overlapping of orbitals. It's talking about sigma and pi bonds. It talks about preventing the rotation and leading to structural isomers. I doubt they're going to ask you about this particular part of it, but you will learn about it more when you get to college.
What's an isomer?
An isomer, that's like what I was talking about, where if the things are on the same side, we call it one isomer. If they're on the opposite sides, we call it another isomer.
Wait, what's on the same and
Remember an isotope was same type of atom with different numbers of
This
neutrons?
is like same type of molecule.
It's the same molecule. It has the exact same chemical
Just like different
formula,
formation.
different arrangement in 3-dimensional space. That's what an isomer is. Same chemical formula, different spatial arrangement. What they probably will ask you to do with sigma and pi bonds is to talk about, if you're given a particular molecule, how many sigma bonds and how many pi bonds does it have? Well, these 2 bonds are both going to be sigma bonds because they're occurring from the sp2 of this carbon overlapping with the 1s of this hydrogen. And that overlap occurs right in between the 2 atoms. That's what we call a sigma bond. So there's a sigma bond here, same thing here, that's going to be a sigma bond. And those are also going to be sigma bonds. I'm just not going to draw them because it'll make my picture look really nasty, okay? There's other sigma bonds. I'm going to draw the other sp2 hybrid orbitals in a different color. These 2 sp hybrid orbitals between the carbons overlap and make another sigma bond. Right? So this molecule has 1, 2, 3, 4, 5 sigmas total. I drew some in green and some in orange, but they're all sigmas. And then it also has that pi bond, which again I can't draw very well, but it's an unhybridized p from this carbon, an unhybridized p from that carbon, overlapping in a region not directly between the two nuclei, but it's still going to cause attraction of both of the nuclei to a region that's, you know, sort of in between them. It's going to help hold those two things together. But this is called a pi bond. So this thing has 5 sigmas and 1 pi in it. Basically, if it's a single bond, you can count it as a sigma. If it's a double bond, you can count it as 1 sigma and 1 pi. If it's a triple bond, it's 1 sigma and 2 pi's, like we saw in that last diagram with C2H2. Woo! We didn't even get to molecular orbital theory. Good thing you don't need it for the problem set.